Okay, also, it's my great honor to give a talk like very, very well talented and very promising young researchers like you. So actually, I am very proud because he was a student, like undergraduate student when I met him for the first time. But now he's very well grown, already very promising. Okay, so this is a colloquium. Today, I don't want to go deep inside. I just looking at the outside of the theory of partial differential equations. My main purpose for this talk is to introduce you what is the theory of partial differential equations and what kind of subjects now are like available in many directions. So this is just the introduction, but if you have some more interest in more details, and please feel free to contact me, and I can talk with you personally, likely very serious problems also. So, okay, here the title, even though this is the title, very specific topic, but I am going to this topic only in later, like the last 10 or 5 minutes. Okay, again, this is a very, very introductory like a subject in this case. Okay, so let me start with the PDE, right? So because this is the PDE. Then what is PDE? PDE is the equation. Okay, having a known function here, more than 2 variables, that is partial derivative, and certain over is partial derivative, right here. So PD is the equation, and I have the U. U is the solution, and the combination with the is derivatives. Okay, so the order, the largest number is the order of PDE, and the structure is the function capital F here. So what kind of PDE the form actually depend on this is capital F. So F is given, it means that you have the PDE. And the solution means that we find the U, verifying this identity. But what kind of sense? That is also important. Of course, to discuss about like the uniqueness and the uniqueness, usually we have prescribed this is boundary conditions. Okay, for the linear problems, usually we have an explicit formula, but most of our nonlinear PDE, we don't have an explicit formula. Instead, we have many beautiful theory to guarantee that we have the solutions, uniqueness, and some other properties. Okay. And then the question is why? What is the purpose of a PDE? Right? The first one is like a PDE is fundamental to a lot of different subjects. Right? So that's why the public comes. Also, we have many applications like chemistry, engineering, environmental science, biology, also data science and engineering. Simply because the PDE is a representation of many natural physical phenomena in this real world. And also, of course, uniqueness and existence are important because you are mathematicians, right? The convergence is important. And the limit directly related existence and uniqueness. Probably the biggest area of research in PDE right now is nonlinear PDE, right? In terms of like a general theory, like such as symmetry analysis and perturbation analysis or stability of solutions. blah, blah, blah. So that's why, right, in Korean community, probably the largest community in mathematics is PB related. Like here, you have many talented young professors. Okay, so your future is very proud, as promising. Okay, so now I'm introducing what kind of PDE, the type, equations, just the introduction. Okay, so PDE, the variables, of course, the space and the time. The stationary case means that the solution tends toward a steady state solution. We don't have time variable, only space variables. And the evolutionary case or evolutionary PD means that we have the space and the time. Okay, this is related to the situation that the solution evolves in time from a given initial configuration. That is initial conditions. And so variables X only, that is a stationary case. Together with the time, that is evolutionary case. And then the time. So stationary case, we usually call that is elliptic PDE. And the parabolic case, time one derivative, but the special twice differentiation, this is hyperbolization. Usually we separate in this case, elliptic and the parabolic and the hyperbolic. There is no precise definitions, elliptic, parabolic, hyperbolic, but usually we classify in this way. And another one is also like linear, nonlinear. What is the difference? The difference is right here, U gradient U Hessian. That is the main basis. The important thing is that is the coefficient here, like X, X, X. If the coefficients only depend on X value, that is a linear parabola. And the semi-linear means that the largest, highest order, the coefficient only depending on X variables. This is a semi-linear. And the quasi-linear means that the highest coefficient only depending on gradient. Otherwise, that's pretty linear. So linear, semi-linear, quasi-linear, pre-nonlinear. Usually, when I was a student, I started studying only linear problems and moving to semi-linear, quasi-linear, pre-nonlinear. So also you can do that, probably in this direction. And then, of course, yeah, sometimes single PD or systems. Single PD means that my solution is the range, is only one dimension, real valued function. System means that my solution has a vector valued functions. But most of the important problems must be systems. Like the example right here, Maxwell equations, Navier-Stokes equations, or Einstein-Friedel equations. Of course, to solve systems, you first have to understand single PDEs. Okay. And then also, the form of a given PD is very important. And so there are two types. One is here, divergence. Divergence. And this is a vector, valued nonlinearity, and the gradient, very likely, usually in this way. And another one is non-divergence, like Monchanta intentions. So, assuming that you are studying PDE, then probably you have this type or another type, because the style, how to study is really depend on what kind of type you study. Like here, this is a divergence form. Then the meaning, the identity, the solution. How can you understand the solution? Usually we need to say here, the integral. That is a weak solution. Distribution or something like that. But for this case is non-divergent form. Usually we understand this identity in terms of the pointwise. That means that the different concept of a solution should be applied, like viscosity solutions. So of course, it really depends what kind of study, what kind of are you studying. So usually I do study both types. But my main type is here, divergence. Okay. So also there are PD. Why many mathematicians are studying? Because there are so many problems, right? There are so many types. There are so many boundary conditions. Also, what kind of boundary condition? Also very important for your study. Of course, the boundary condition depend on the natural phenomena in which you are interested. Okay, so of course, the first condition is here, right? Zero, it does not matter. You just any function, non-zero function. This is theoretically boundary conditions, okay, or Neumann boundary condition. That is kind of some perhaps flow problems, and Robin, that is mixing together, or Average boundary conditions. Also, normal direction, also the slanting direction is sometimes important. Also, conormal activity boundary conditions, we can start. Actually, I studied all of 5 terms I have studied. But to me, it's important. Right now, I'm very interested here. Average boundary conditions. Also, we can start. Probably, this average boundary condition is related to some mathematical biology. I have found so many applications. Then, so once I have the PDE, then of course, what is well called this? Of course, the resistance and the uniqueness. Then stability. Stability means that the solution depends continuously on the given data, given in the problems. If we have all 3 items, then we say that the PDE has a reinforcedness. The distance, uniqueness, and the stability. Okay. Now let's go to the why we are studying in the theory of partial difference equations. Usually, it started from the Hilbert problems, 1900 in ICM at Paris. Starting from here, many of PDE can be derived in a variational. That is by a minimization of an energy function. Okay, then Hilbert, 19th problem is here. Are the solution of regular problems in the calculus of variation always necessary analytic? This is the regularity. The title, my topic is the regularity. I have solutions. The real question is that the solution is really a negative. That is, of course, usually not. And of course, this is a result proved by George and also Nash, 1957 and 1958. And then the second 20th problem is about to all variational problem with a certain boundary conditions have a solutions. This is the inexistent problems. So this is of course partially resolved This is also a significant topic of research throughout the 20th century up to now. So, culminating in solutions for the nonlinear cases. And so here, 19th regularity issues and the 20th logistic issue. And the last of his silver 23 is a further development of the calculus of variations. But this is the two main to this stated result. So the regularity of PD, but isn't right now developing to prove these three problems. Now, then what is the calculus of variations and PD? So this is the energy, pi, I mean P. That is the energy integral or energy density. So we say that the problem is regular means that this pi is regular and convex, usually quasi-convex. This is the definition of regular. His 19th problem is the solution is a nullity. Okay, this is minimized. And then, okay, assuming that U is minimized, then we can derive the PDE. That is called to the Euler Lagrange equations. If you are studying PDE, this is right. You have the energy formula. Then it can be expressed in terms of partial differential equations. So the minimizer is a solution of this divergence equations. Then, before going further, right, to discuss about the regularity, okay, I have to introduce two very important spaces in the PD regularity. You just remember only two spaces. One is the Holder spaces, and the other is the vector spaces. The other is just the small perturbation of the spaces. This is the definition of a Holder space. I believe that most of you know this Holder spaces. Okay, so this is the definitions. So we think about what is the definition of the Holder continuous. Think about the graph of the function. Graph of the function, the shape. The shape is looks like here, this kind of. So you have the graph of the function. Whether you have this kind of shape project, right, outside inside. And this is Holder continuous. And then why this is a Holder continuous is important. Okay, this is definition. The estimate of U in Holder are actually saying that the graph of U is more and more concentrated to a single value. Okay? The concentration in a precisely controllable fashion. Similarly, estimate of U C1 alpha. C1 alpha means the gradient. First, the gradient derivative is Holder continuous. C2 alpha means that the second derivative of U is Holder continuous. We say that graph is more and more look like a linear function or a second order polynomial. It looks like a different. This is a kind of right. This approximation. So it seems puzzling about why he used C alpha Holder space. I don't know precisely, but my point is that the reason is that, like most of mathematics, it is harder to say non-qualitative things. Right? We need some numbers or pictures. Continuity is a very unstable process. But, however, C alpha is a very stable measurement, as any uniform limit of functions with the same order is still enjoying the same Holder continuum. It means that the limiting process, approximation argument, is very stable in the Holder spaces. So continuous is not enough. Think about the Agelas for any kind of theorem. And we need a C alpha. Okay, continuous is not enough. But once we have the Holder continuity of the solution, already the PD is very nice enough. That is a starting point. The Holder regulation. So regularity means that at least my solution is Holder continuous. Okay. The famous theory about dissolving. What is the dissolving? Solution. My solution is Holder continuous. So don't forget about the Holder spaces. It's important. In PD, Holder space is a very fundamental. And another one is LP space. This is a regularity, Holder regularity, but the existence. And in very, very weak sense, weaker solution, then the space should be defined in almost every sense. That means that we need LP spaces. I think that you must know what is the LP spaces. And let's go. So the point is that here, okay, so Holder space is we know, right? Because that is a Holder means that point-wise behavior. But the LP space, the question, what is the typical behavior here in point for the LP functions? But the thing is that here, the fundamental theorem of a logarithmic integral is here. Every element function is almost everywhere continuous, only in the sense of the average. We understand all is in the sense of the average. Holder space is just pointwise, but the LP space, always we try to understand that only in the sense of the average. Then what is the relation between LP space and the Holder spaces? And that is also important. I have a function, Holder continuous. Okay, I have a function just that belongs to LP space. And what is the relation? This is a very famous theory that is called to be, this is a Campanato embedding. This is like here. This is a very beautiful, very beautiful. Even though you have the LP function, but it can be, I can understand in the sense of integral. So this theorem says that we can understand Holder continuous not only in pointwise sense, also in LP nodes. Right? This is the connection, the bridge between Holder space and the LP spaces. Here, we notice that only the averages, not the LP nodes, measure the invariant smallest. Usually in the regulating PD, we always try to understand in the sense of the average. Right? That's why probability and probability theory is really related in the theory of PD. So we can visualize the whole node of U in all kinds of different nodes, like here P. P is any P. In particular, you are studying, when you are studying like nonlinear partial difference equations. This is important. Most of the beautiful theory like Disjoji, Schauder, also here you understand. Okay, you have the solution, that it means the weaker solution. My solution belongs to like the LP space or Sobolev spaces. And how we can go to visualize in the pointwise sense, just by using this Campanato embedding. The now again. So the form I said earlier, the form is important. Okay, there are two types. First one, divergence form and the non-divergence form. Okay, also problems are classified in two cases, the variational problems and the non-variational problems. And Evans' book, chapter 8 is about the variational problems. The book, chapter 9 is about the non-variational problems. So variation means that I have an energy functional of this energy comes from the natural phenomena. This is the modeling. This is energy. And then Euler-Lagrange equation always are in this divergence form. Okay, this is a variational case. But non-variational case, we start directly from the PDE. It means that if there exists no energy integrand such that, and the non-divergence form is right here. So maybe you can start this energy whenever you are studying, or you can start this non-variational PDE, non-variational also, you can start non-divergent, like example equations. So if you are, like right now you're studying PDE, you probably 1, 2, 3, you have studied this. Then first look at the divergence problem. Then how I can understand the identity, the solution. Usually divergence form means that I'm trying to understand in the sense of the integral. It means that you just take a test function. Okay, take a test function and multiply to PDE and take the integration by that. This is the definition of a weak solution, like a duality argument. So, if the right-hand side is good enough, then I can understand in the sense of the weaker solution. This is the definition of a weaker solution or energy solutions. But the situation here, the right-hand side F does not have enough higher integrability, like the measure or L1 space. And we need a more generalized solutions. That is like very weak solutions. This is very generalized solutions. In this case, approximation is very important. Not energy solution, that means that entropy solution. Well, normalized means that even though this is not good solution, but I can pre-assume that my solution is already found. I can add one more conditions, then I can define here. We normalize solutions, approximate solutions. This is a different kind of solution. They're also solar. So if the PDE, given PDE, getting more general and general, we need to introduce more general concept of solutions. Right now, is the theory of the PDE is going to narrow. It means that we need a more general sense of the solution. Must be developed. And so for me, actually, I started like here, weak solution, and then here, solar solutions right now. Also, like if you are very difficult, including the existence, then why don't you try to extend the concept of solutions, and you might have a chance to discuss about the existence. And then observability, right? If most of you are young students, right? Of course, the most important, how I can prove the existence. So far, there are many well-known approach to discuss about resistance. Right here, I introduced many, like log-milligram, parabolic, compact operators, probably know. And for the evolutionary problems, like Gander-King approximations, one comes from the calculus of radiations. And also for the nonlinear PDE, usually we use like here, monotonicity and the fixed point. It's kind of the, if the PDE is non-divergence form in the point-wise sense, then this kind of like Heron's method maybe is also the continuous. Okay, anyway, there are many approaches are still developing. But at least if you are studying, I believe that you should know all the. Okay, if you know that is very tough. Of course, yeah. Whenever I have the PDE, I'm thinking what kind of approach I have to use to prove the existence. And then regularity, right? Once the issue of the resistance is resolved, the next question is, I have the solution. But that is a very, very weak concept of solutions. Then the next question, my eventual goal is that my solutions are valid. How I can prove that? That is the issue of the regularity. I'm starting C alpha. And then C1 alpha, C2 alpha. So likely W2P means the non-divergent. I can talk about the Hessian second derivative. Better. As it belongs to LP space. That is W2P. So you have the PDE. Regularity means that most of regularity means that is it all the continuous C alpha, C1 alpha, C2 alpha, or W1B, W2. Okay. Also regularity. I'm talking about the local problems. So you have the domain. The PDE, I can localize. So which location interest? Right? There are three cases here. Interior case. I don't have only inside I am interested. That is an interior case. And the second case, usually I only interested in on the boundary. That is the boundary. Or altogether. That is a global. So also regularity, sometimes interior or boundary or global. So if you look at some papers only interested here. On the boundary, what happened? And then right here, there is always a regularity is always very difficult, very difficult regularity issues. Right here, I have this is a divergence of PDE. Then starting point is usually starting point is elliptic. Because usually solution is not guaranteed to be uniform. So first I need to prove boundaries. Then like a Cacciopoli, boundaries comes later. And then of course the harness. Harness means that I have solutions. Harness means that two values, two different values. Are they discussing each other because you satisfy the solutions? That is harness. Important. And then go forward. Lipschitz, C1 alpha, C2 alpha. Starting from L infinite, going up and up. Because sometimes this process is really different. It depends on what kind of coefficient or what kind of boundary conditions. Also, if you are studying like here, this is a non-divergence form. And the most important thing is that ABP maximum principles. Because here I try to understand the identity in terms of a viscosity sense. Point-wise or eigen sense. So that is ABP maximum principles. I think that there are many papers. Also, this is a special case here, separate in this way. Recently, I have some papers here. So singular means the gradient U, right? This gamma is a positive. And the gradient U goes to zero, means that this time goes to zero. This is degenerate. And the gamma is negative, that goes to plus singular. Can you prove the solution still satisfies C1 alpha? Because C1 alpha the best one. Very recently, this was approved. But of course, also you can generalize this. And so here, usually the definition of a degenerate singularity, it depends on the PDE. Okay, in this case, gradient coefficient goes to. Okay.
Well, even the gamma is even smaller than -1.
It does not make sense.
That makes sense.
Usually we cannot discuss about the solution. That's fine, I know gamma is less than -1. Well, you can start in the P-Laplacian problems. Okay, so assuming that everything nice, just differentiate. And the P-Laplacian case, the energy must be P bigger than 1. And if you look at that here, that means they cannot be the -1. Ideal case. So the question seems like the P-Laplacian problems. The question is, if a P is less than 1, then what kind of solutions? It might be not easy, right? Because LP space P less than 1, and how I can understand.
So in the energy, P greater than 1 corresponds to the convexity of the integrand in grad U. This is
I mean, P-Laplacian or this
P-Laplacian case.
P-Laplacian.
Yes. So does that P greater than 1 condition corresponds to the convexity of the energy functional?
P-Laplacian case, I don't know. That is maybe degenerate or singularity. So P bigger than 2, that is a degenerate problem.
Degenerate equation, yes.
Oh, okay. So another regularity issue is also maybe some of you are studying here. That is obstacle problems. I can add this condition here. Solution is pointwise bigger than some obstacles. This is naturally related to P-value. And so this is also hot topic, one of the hot topics. Well, asymptotic problems is so gradient U. We are only interested in gradient U is large enough. And gradient U is bounded, then already ellipses. And the asymptotic means that what happens, gradient U is sufficiently large, or even Hessian U sufficiently large. And the question, with a very small perturbations, can you change and this really non-regular problem into regular problems? In this direction, also it is. Also, another one topic is the right-hand side in the measure. I almost L1. Right? And can see we have some fractional higher integral. Of course, this is the typical problems like this is here, potential estimate also very important. And also double and phase problems. So I will talk about double and origin phase problems. Okay, so there are many problems here. So here are the topics. At least I have more than one pages each areas. So I have tried to solve many problems just because I have so many students. I need many more problems. You study like abstract problems, you study like a non-divergence problem. Yeah. But to me, this is a interesting problems. Also, metadata problems, if you are interested in metadata, it has lots of many applications, like mathematical biology. Okay. Again, another topic is here. So problems can be classified like here, local problems and non-local problems, and mixed local and non-local problems. So what do you mean by local problems? To look at, right? I have the solution. I want to know what will happen at the specific point on the point X. And I only local problems, it is enough, it's only looking at the neighborhood. That is a local problems. Most of the PD problems, local problems. Non-local problem means that even though I only looking at the information like here, the position I am standing here, but I need a far away problems. That is a non-local problems. Then what happens? It mixed together. That is non-local. So actually, I have started with the local problems, and then very recently, like 2 or 3 years ago, I have started with non-local problems. Then the natural case, what is happening? Mixed together. That is a mixed problems. So maybe also try to, if you are interested here, also here, non-local problems is a very interesting problem. I think that if you are very young, you should have non-local problem. I strongly expect to start non-local problems. Okay. So local problems, again here, I introduced already very ancient problems. Actually, local problems is also classified. I started here, this energy. So the energy growth condition, right? You have the energy function, and looking at what kind of growth do you have? The first one is standard growth. Standard growth. Energy is just the LP energy, means the P Laplacian problems. This is standard, this is energy, and this is the typical P Laplacian problems. This is the model for the nonlinear problems. Of course, we know that the best regularity is a Seoul. So most of our nonlinear problems is just a perturbation of this P Laplacian. This is already very established. Then what will happen? Non-standard instead. Right? The growth is P energy and the Q energy. I have a P Laplacian, another one Q Laplacian, and the energy is moving from P energy to Q energy. This is non-standard. Why we are studying? Because it has many applications, like anisotropic material such as wood, fiber, reinforced plastics, concrete applications. Okay, there are many energies right here. This is called to be G Laplacian problems. This is like some convex function, like this is the example. Alpha equals 0, this is the typical P Laplacian problems. That's small perturbation, right? Then the growth condition is non-standard. Maybe it's not too difficult, but of course, this is natural generalization of the Laplacian problems. And the question is, can you prove a Seoul regularity for weak solutions? Of course, we need some conditions on this function. Like it's called to be like the beta 2 novelty conditions, and we can finish. And another one is this topic was also very popular in last 20 years. The exponent is the function of here. Okay, this is a constant, that is a P Laplacian. In this case, P of x is the function. Then the question is, what is the natural conditions on P of x to guarantee that my solution is has a Seoul regularity? But already we know that is called to be log-Holder continuous. And you know, right? Many kind of continuity, right? Do you have anything like a team? I am studying team, right? Team. And the log-Holder, and the ellipsis, and the log-Holder. But the log-Holder continuous. If you have an exponent, then log-Holder continuous is naturally field. Why? Well, you can compute here, but if you are interested, I can tell you. And then another one is more perturbation. Right? It's a px energy and multiplication of a logarithm function. Logarithm is just a small, a little more small perturbations, but still we can prove Seoul regularity. And then, yeah, this is just you say just very, very small perturbation of P Laplacian. But the property is relative. P Laplacian is a standard growth. It means that it has a uniformly elliptic. But this kind of a non-uniformly elliptic properties. It used to be, it seems very difficult, but right now, no, this is a really easy problems. And then let me go to the non-local problems. Local means that my derivative is 1, okay, just natural. The energy is gravity. Non-local means the pressure, right? Fractional derivative. Right? Then how can you understand the fractional derivative? That is always different quotient or in terms of like here, integrations. This is integration. I want to know the information of x here, because my integration, y is here, everywhere. That's why this is called the non-local problem. So we can think about it. I'm studying x. So I need to know what happened near my point. That's a local problem. Another thing, what happened power wave? This is a data issues. So non-local problems, more important than is the like delta issue. Usually the delta issue is, I mean, according to my experience, first I was very afraid to study non-local problems. Okay? If you are just studying stuff, this is just a small perturbation. To me, small perturbation of the local problems. The only problem is how can you handle the delta? Of course, this is. So the definition is the same, already the same. I have the non-local problems. First, the question is, I have the definition of the solution. Then how can you select a test function? Okay, that is first one question. Of course, it is not easy, but if you are looking at very carefully, you might find a correct test function. And then multiply the test integration by that. And separate the local part, neighborhood part, and power law part. Then interior part, I mean, the local part is already I'm not very well because the local problems. Here, the Pelton part is seems difficult. What we do, try again. Sometimes it will happen. I can solve. You could solve the process. But still, I'm not expert. I just starting from here. But right now I'm not afraid of this non-local problems. Okay, the mixed problems is an interesting issue. Actually, the mixed problem is more easier in the sense that, like here, you have here this is P operation, and this is other term, but the condition is P. Okay? This is the P, like in the P times one derivative. Okay, this is X personal number and the Q energy. The condition is P is strictly bigger than SQ, means that the second term is the lower order. And you think about it, you have the second order P. The lower order term is not important. I have to scale because it disappears. So actually, this is a mixed local non-local problem. It's just a local because this is the later part. Okay, this can be handled as a low order. So the regularity is literally the same as the only local problems. But the Seoul regularity only proved the last year. The observation is not too easy. Yeah, because I have some papers in this mixed problems. And then, so how many minutes? Okay, this is actually the topics. Actually, I wanted to discuss here. But the problem under consideration is here. This is M. Okay. Mx is a given matrix space. So M over X is a matrix. That is the only difference. If M over X is a constant, then this is the user. The question is theta. This is a typical example. X to delta. So assuming that you are standing at X equals 0, and the delta is positive. Okay. Then the coefficient goes to 0, right? This is called to be degenerate. And what happened delta? Delta is negative equals plus infinite. This is that's why this is singular problems. Because of this one, this is not elliptic problems, uniformly elliptic problems. The only difficulty you have is problems. But I know that if delta is moving minus n plus n, still I can prove a C alpha. It was a trouble in 1980. And then the difference. The thing is here, okay? M of X has a degenerate in this relation. Okay? And the M over X is constant. And we have a very low level. The question is, what is M over X is given just a given matrix. So constant, I have a regularity. Variable, then I can generalize at some point, right? Still, the regularity is working. And beyond some range, there is no way. The question is, how large is that here? So this is also one of topics that I am focusing. So assumptions here. Because omega is a very non-smooth domains. And A without here, MN, that's the elliptic parabolas. Okay. Uniformly means that here I have the constant. Okay. If this is a positive definite, means that the eigenvalue is a strictly positive, that is uniformly elliptic problems, then everything is well known. But the question is sometimes it touch zero or infinite. Then how can you solve these problems? The hope is that we regard this matrix just the weight measure. If I can move on this matrix to the measure, then I can still discuss about the existence in the weighted Sobolev spaces. So that's why the weight, movement of weight comes naturally. So this is a matrix, and this is a scalar weight, and this is a given problems. And like here, okay, if you look at this monotonicity property, okay, my matrix and the Kg actually represent gradient of the solution. So matrix and the gradient of the solution, they are fitting together. We cannot separate. If the problem, the matrix is a positive definite, you can separate. The only difficulty is we cannot separate. All is put together, but still it doesn't make sense. Okay, the thing is that I have if this is a constant, if this is just a linear problems, H1 or non-linear problems, but I added this weight, and I extend the concept of solution, the space. And from here, we need one more conditions. Weight, so whatever space, the weight must be Munkenov weight. That is A2 class. Then the Munkenov, if I looking at the Munkenov weight, that is related to the BMO space. Right? You have the weight. And then very well-known problem is if you take a logarithm function, then it is a BMO space. So you can observe that. What is the regularity condition on the matrix? Right? Just first take a logarithm function and take a BMO. If that is sufficiently small, then the problem is almost just a regularity. Okay? This is the simple idea. But sometimes it is working. So this is a perturbation argument. I have the variable matrix, then I need a frozen argument. That's why first take a logarithm. And I need going back to by taking explain it. Now this is called to be logarithm average. Okay, there are many sense of averages here. But in this case, logarithm average is working. Okay. M is starting point is mx is a variable matrix, and then frozen. Okay, and then frozen. That is a constant matrix. Of course, that is definitely positive definite matrix. And compare two problems. If the difference is not too enough, okay, then I can still recall at least reasonable as some content of the regularity issues. This is the one. So in this way, right now the regularity theory on elliptic and the parabolic problems is highly developed for the uniformly elliptic problems. But still, if the problem has some degeneracy or singularity, and is wide open, there are many open problems. But this is one idea how you can handle a degenerate singular problems. Of course, by adding the matrix weight there, we can consider, yes, consider more and more channel PD, class of PDs. So I think that this is the, and that this is the population. I am starting degenerate problems and then comparing the elliptic problems. Then try to compute the difference. That is, we need there are many well-known approaches. That is qualitative comparison. Usually, we are looking at the functional analysis. We are looking at the like harmonic analysis, also sometimes the geometry analysis. If you are very familiar with many kind of areas, still you can go forward. This is a population argument. Okay. So this is the okay. If you have
Any questions?
I have two questions.
Yeah.
First is, only divergence problems can be cast in variational problems.
yes.
So,
Of course, yeah. Non-divergent, of course, you can start in the area like optimal transport. So this is, I think, different.
so are there many PDs which cannot be cast in variational problems?
I think so. Only divergent form is very natural.
And the second question is, how do you find a regular function?
Oh, okay, it's a good question. Then my definition is at least the whole continuous. That is a good plan. But it depends on. Sometimes the regular means that at least the differential one, but then here I would say all the continuous is there.
Is it standard definition?
No, not the standard. There's no definition regular, right? It depends on each person. So how about you? What is your definition of a regular function?
Measurable and finite average or variance. That's, I don't know. Yeah.
At least, right? So solution. Solution has some at least the minimum property. Right? It's better than minimum regularity. It should be called.
You mentioned the P Laplacian equation with measure data. I'm wondering that the P Sobolev regularity is still true for arbitrary measure mu.
Yeah, I only need a signed random measure.
Wow.
That is very minimal. No limitations. Almost L1, not much difference.
And this Lado measure can also have this point masses. So
My solution has some solution. Likely, I mean, yeah, inside, right? Inside, usually you say gradient tube. My gradient tube belongs to almost W11 space. Then Sobolev embedding, and still gradient U has some higher integrity.
So you mean even if the right-hand side measure has direct points, your solution has some.
Likely, think about it, just the fundamental solution.
So fundamental.
Fundamental solution, of course, you can differentiate at least twice. Typically, example is a fundamental solution.
Any other questions?
And I am wondering about the LPX space. We assume that PX is bounded in two constants, gamma 1 and gamma 2. But what happens if PX increases to infinity?
Oh, okay, that is a good question. Okay. So usually that is like the infinite Laplacian. So the limiting case one, that is the one Laplacian. The other case, the infinite Laplacian. Infinite Laplacian is usually like there are many applications. That is a typical non-divergence elliptic problems, very close to curve over world problems. Or actually viscosity solution perfectly match with the infinite Laplacian. You just look at it. He used curve over games like that. That is a driven game. Actually, one of my former students now, he's now postdoc at Finland. He's working with infinite Laplacian, including this curve over world.
It also, but I think I also heard some nice talk of Evans on this infinite Laplacian.
Oh, yeah. If you go to the Google, and very short notes.
Any further questions? Okay, if not, let's thank the speaker again.